In this video, I'm going to be running through a bunch of different proof shortcuts. Now, this is not a comprehensive video because, as you'll see in a minute, it would be impossible to be comprehensive about different proof shortcuts, but I will run through some of the more famous ones, and your practice problems will be about some of these. So even though we won't get to practice with them in Carnap because Carnap doesn't have them natively programmed into it, we will still have some questions about these shortcuts in the practice problems for this week. The basic rules that we learned last week tell us how the system works. There you can say the rules of the game. Derived rules, though, tell us how to skip through some of the steps in some tedious proofs. This means that they're never essential, but they can be very helpful in speeding up our proof. And sometimes they let us see proof strategies that might not have been evident beforehand. So in fact, they're all going to be proven using the basic rules, as I'll show you, or it can be proven using the basic rules. Some of them turn out to be more complicated, and I'll have time to go over in this video. Which means that we can always recreate their proof inside of one of our proofs and then use it. That would just be really tedious though. So instead what we do is we give it a special name and then we appeal to it as we appeal to the basic rules. So you'll see how this works in just a minute. The idea is they can be helpful because proofs will often exhibit similar chains of reasoning. And if we can capture that chain of reasoning into a derived rule, we won't have to repeat it over and over again. In fact, any proof you've done so far, you can give it a special name. You can even call it your own name. And you can appeal to it in any further proof. It just might not be as useful as some of these other derived rules will be. Okay, so here are the derived rules that I will go through in this video. You can see your book for more examples, but these are just the ones that we'll need, that we'll be working with in the remainder of the class. The first is double negation elimination. Then we'll have contradiction, disjunctive syllogism, De Morgan's laws, and modus tollens. So let's start with double negation elimination. The idea with double negation elimination is that from the well-formed formula negation of phi, we can infer phi. This is actually what your book has been calling negation elimination. I won't give a proof of this here because it's either very long or it relies on other derived rules. The way that we would appeal to it is that we'll abbreviate it as DNE, and then you'll write the line number of the double negated well-formed formula as the justification for the well-formed formula phi. We'll see this rule in action in just a minute, so you can see how it'll work in just a second. The second one is known as contradiction. The idea here is that from the well-formed formulas phi and negation phi, you can infer anything you want. So this is a little bit weird of a rule, and it's often summarized as from contradiction, anything follows. So the idea here is like, if I can derive a contradiction in my proof, something has broken already, and so I can conclude anything that I like. It's really important though that it's a true contradiction. So you have phi and negation phi, that like one of them isn't inside of a subproof or anything like that. Okay, so let's see how I would prove this rule. Suppose I have the two things that contradict each other. I have P and negation P. I can have them as assumptions or as somewhere in my proof. Then what I'll do is I'll hypothesize anything that I want. So suppose I want to conclude Q. I'll hypothesize the negation of Q. Now I can write the bot and say that there's a contradiction on P and not P. Q has nothing at all to do with the contradiction that I'm going to show. From that contradiction, I can derive the negation of the thing that I hypothesized. So in this case, I would derive the negation of Q. And here's double negation elimination in action. From the double negation of Q, I can derive Q. And this is just how I would prove contradiction. We'll actually see contradiction in action as well in just a minute. So if you're not sure how to use it, you'll see it work in just a minute. Okay, so our next rule is called disjunctive syllogism. As the name implies, a disjunctive syllogism requires a disjunction, and so what we'll do is we'll start with the well-formed formulas phi or psi. And suppose that we don't have phi, so we have negation phi, we should be able to infer psi. The idea here is just, if you have a disjunction, one of the disjuncts has to be true. If it's not the first, then it must be the second. You can also say that if it's not psi, then it must be phi. So if you have negation psi, you can infer phi. Okay, so how would we prove this? So we're actually going to use a disjunction elimination because we have a disjunction as one of our premises. What we want to show is that P implies Q and Q implies Q in order to do a disjunction elimination on P or Q. Well, how are we going to get that P implies Q from this disjunction? We're actually going to use the contradiction rule that I just introduced and find a contradiction, and then we're going to be able to say P implies Q. So how's this going to work? Well, we're going to hypothesize P. We're going to find that we have a contradiction on lines 2 and 3 because we have P and the negation of P. Because we had a contradiction, we can write anything at all that we want on line 4. In this case, I'm going to write Q. On the next line, I want to be able to export some of what I've done in this subproof outside of the subproof. So I'm going to do a conditional introduction on that subproof to get P implies Q. Remember, my hypothesis for that subproof was P, my conclusion was Q, and so I get P implies Q. So we're halfway to a disjunction elimination. Now all I need to do is show that Q implies Q, which should be pretty easy. I'll do it like this. I'll hypothesize Q, I'll repeat Q, and then I'll do a conditional introduction on the next line to say Q implies Q. So if I have P implies Q and Q implies Q, I can conclude Q because I can do I can eliminate the disjunction on line 1 with lines 5 and 8. This is how I prove the disjunctive syllogism. This is a little bit of a strange proof, but you'll get used to using the contradiction rule as we continue on. The next set of rules is De Morgan's laws. So there's actually 2 biconditional statements that constitute De Morgan's laws. The first is that the negation across an or implies the negation of each of the constituents put together with a conjunction. So the negation of phi or psi implies negation phi and negation psi. And this works in reverse too. So if I have negation phi and I have negation psi, I can conclude negation of parentheses phi or psi. The other part of De Morgan's law is that negation of phi and psi implies the negation of phi or the negation of psi. And the reverse, negation phi or negation psi, implies negation parentheses phi and psi. The idea here is just that when we distribute a negation across an and or an or, they flip to an or an and respectively. Similarly, if we want to pull out a negation, we'll have to flip an and to an or an or to an and. Now, if this looks kind of familiar, you're right. On problem set 1, you gave the truth table for the first. So we had in that problem negation across an or, A or B, and we showed that that was equivalent to negation A and negation B. I hope on that problem set that you indicated that was in fact a tautology. So I won't have a proof of this because we'll have a proof of these in our practice problems for this week. Just remember, when we want to distribute negations, we'll have to flip our ands to ors or ors to ands. The final derived rule is called modus tollens. Modus tollens works like this. If you have a conditional statement like phi implies psi, and you have the negation of the consequent, negation psi, you can infer negation phi. So for anybody that's familiar with the contrapositive of a statement, so if you have phi implies psi, the contrapositive is negation psi implies negation phi. Modus tollens is just relying on that contrapositive. So negation psi implies negation phi. This one's actually pretty famous in philosophy, so here's an example of what it looks like in practice. If the dog detects an intruder, then the dog will bark. The dog did not bark, therefore no intruder was detected by the dog. In this case, we have if the dog detects an intruder is phi, then the dog will bark is psi. The dog did not bark, so we had the negation of psi. Therefore, no intruder was detected, so negation of phi. And you'll see plenty of appeals to this kind of argument pattern in your everyday life. Okay, so let's see what a proof of this looks like. So we know that we have two premises. Say that we have P implies Q and negation Q. What we want to derive is negation P. So in this case, my conclusion has a negation, which means I'm likely going to have to hypothesize the conclusion without the negation, derive some kind of contradiction, and then do a negation introduction. This is in fact what I do. So I'll hypothesize P, and then I'll notice that P implies Q from line 1, so I can do an elimination of the arrow on lines 1 and 3 to get Q. And then I notice that I have a contradiction. So I have negation Q on line 2 and Q on line 4. So I can write bot eliminating the negation on lines 2 and 5. So I derived a contradiction inside of my sub-proof, which means that the hypothesis for that sub-proof was incorrect. So I can conclude negation P by the introduction of a negation. So what I've shown is that if P implies Q and I don't have Q, then I don't have P either. Okay, so here's the full list of shortcuts or derived rules that we'll be using for this class.